You're listening to DTFHN for April 2nd, 2026. I'm your mass-produced yet artisanal host, Jack Haxman. We are your daily tech feed for Hacker News, a website where mass extinction events and font rendering bugs receive roughly equal emotional investment. Today's a day a guard keeps cracking open, and the builders keep walking through. Let's get into it. IBM is running ARM binaries on mainframes. Let me say that again, because the press release buries the under 14 layers of enterprise adjective soup. Someone submitted a Linux kernel patch today. KVM as Sungolio introducing ARM 64 virtualization. That means IBM C mainframe. The same machine that settles half the world's credit card transactions can now spin up a virtual machine running ARM code natively, or close to it. Pull this thread and it gets fascinating. IBM has spent decades building what is arguably the most reliable computing platform on Earth. 6 nines of uptime, hardware-level encryption on every byte, hot swappable everything. Processors, memory, I/O cards. You name it. The engineering is genuinely beautiful. But the software ecosystem is small. Always has been. That's the trade-off when your architecture is bespoke. ARM, meanwhile, has the opposite problem. Massive ecosystem. Every phone, most cloud instances, a growing chunk of edge and AI inference hardware, billions of devices running ARM code, but ARM doesn't have anything that touches mainframe-grade reliability. Now, imagine combining them. You keep the Z's extraordinary system design. The redundant everything, the cryptographic coprocessors, the I/O subsystem that was doing what SmartNICs claimed to do before SmartNICs existed. And you open it up to the entire ARM software universe. A developer writes code targeting ARM, deploys it, and it lands inside a mainframe security perimeter, running against mainframe resident data, with mainframe-grade availability. The application comes to the data instead of the data leaving the vault. One of the Hacker News comments nails the real question. Does IBM eventually migrate Z itself to custom ARM cores? The value was never the S390 instruction set. It was the system architecture around it, the cache coherency, the error correction, the firmware stack. If IBM can maintain all of that on ARM silicon, they get access to the entire ARM toolchain, the compiler optimizations, the developer population. That's a long game worth playing. And here's what matters from a bootstrapped-in perspective. This is landing as Linux kernel patches. Public, reviewable. The virtualization layer is being built in the open, through KVM, where anyone can read the code and understand exactly how the architecture bridge works. IBM could have done this as a proprietary hypervisor extension. They didn't. The most reliable computer ever built is opening its doors to the biggest software ecosystem on the planet. That's elegant engineering meeting ecosystem. Gravity, and the result is more choice, not less. Open systems win when people can choose, pause, and it turns out millions of men are making exactly that choice with their screens right now. Buried in Ofcom's latest report on UK adults' media habits is a number that deserves more attention than the headline got. The regulator found that men are leaving broadcast television for YouTube, not supplementing, replacing. And the framing of the report tells you everything about where the regulatory mind goes when people start choosing their own information diet. The question nobody at Ofcom seems willing to ask is this. What if broadcast television was the anomaly? For 60 years, a small number of editors decided what millions of people watched, when they watched it, and how it was framed. That's not media, That's a bottleneck. YouTube, for all its problems, and there are real problems, is architecturally different. The recommendation engine is flawed. The clickbait is exhausting. The incentive structure rewards engagement over accuracy. The comments on this story make that clear. People are tired of algorithmic slop. But the fundamental shift underneath the complaints is worth admiring from an engineering perspective. YouTube built a system where a person who wants to learn CNC machining at 2 in the morning can find a 4-hour deep dive filmed in someone's garage in rural Ohio. A system where the person who made that video can reach an audience without a commissioning editor, a broadcast license, or a distribution deal. One commenter put it plainly. They ditched TV 15 years ago, mounted a monitor on the wall, and never looked back. That's not a trend. That's infrastructure obsolescence. The AI companionship angle in the report is worth pulling apart too. People are building relationships with language models. The instinct is to pathologize this, but run it forward. If someone can talk through a problem with an AI at 3a.m. instead of doom scrolling, that's a net improvement in human agency. The tool exists. People are reaching for it. The interesting engineering question is whether those systems stay open enough for users to understand what they're interacting with, or whether they become another black box optimizing for retention. What worries me about Ofcom's framing isn't the data. The data is fascinating. It's that a regulator built to oversee broadcast licensing is now cataloging how people use YouTube and AI chatbots. The architecture of open platforms is what makes them powerful. 1,000 creators building freely will always produce more signal than a commissioning board selecting 12 shows for autumn scheduling. The tools exist. People are choosing them. The real question is whether regulators will respect that choice or try to rebuild the bottleneck. So what happens when someone decides to bring a beautifully weird programming language into the belly of the enterprise beast? I once spent 3 weeks building a rules engine in Java. Interfaces, abstract classes, visitor patterns, factory methods. The whole cathedral. When I finally showed it to the domain expert, she looked at the screen and said, "Can I just write the rules in a text file?" She was right. The entire architecture existed to work around the fact that Java makes it painful to treat data as a first-class citizen. Engineer at Michelin. The tire company arrived at the same conclusion, except he actually did something about it. He needed a system for manufacturing reference data, business rules that change constantly, data structures that evolve with every new product line. The kind of problem where object-oriented languages don't fail dramatically. They fail slowly under the weight of their own boilerplate. He picked Clojure. And the interesting part isn't that it worked. Of course it worked. Clojure has been production-ready since 2007. The interesting part is watching someone walk through the logic of why, and realizing the argument is airtight. Follow the thread. You need business rules that non-engineers can read and modify. You need a DSL. A domain-specific language. In Java, building a DSL means writing a parser, a lexer, an AST, a runtime. In Clojure, you declare a variable. That's it. The rules engine he built is literally a nested data structure. Rule sets, conditions, actions. All expressed in EDN, which is just Clojure's native data format. The language and the configuration are the same thing. Code is data. Data is code. This isn't a philosophy, it's a compiler feature. Take the enterprise objection to its logical extreme. We can't use Clojure because it's not standard. Standard meaning Java, meaning Spring Boot, meaning 6 layers of abstraction to validate a field. The standardness is the problem. You're spending engineering hours maintaining the scaffolding instead of expressing the domain. Michelin makes tires. Their competitive advantage is rubber compounds and tread patterns, not whether their rules engine uses the abstract factory pattern correctly. The comments are telling. People who've written Clojure professionally describe it like something they lost in a breakup. Left when I changed jobs, not because I wanted to. That's not how anyone talks about Spring. Clojure runs on the JVM. It calls Java libraries. It deploys to the same infrastructure. The only thing it removes is the ceremony. And the ceremony was never load-bearing. It was just familiar. Michelin figured that out. A tire company building manufacturing systems. In a Lisp, the tools exist. Some enterprises are brave enough to use them. Bravery looks different at every scale, from rewriting your stack in a Lisp to strapping humans onto the most powerful rocket ever built. The strongest case against flying Artemis true goes like this. Artemis, I came back with heat shield erosion that engineers didn't predict. The charring pattern deviated from models. Nobody has flown a crew on this system before. And now 4 humans are sitting on top of it. Maciej Shagulowski wrote a detailed argument that this mission isn't safe to fly, and the commenters shared it minutes before launch. That's the steel man. Take it seriously. Now dismantle it on its own terms. Every crewed spacecraft in history has flown with unresolved questions. Mercury Redstone 3 launched after a series of test failures. Gemini had fuel cell problems. Engineers were still characterizing. Apollo 8 sent 3 people around the moon on the Saturn V's first crewed flight, with exactly 1 prior uncrewed test. The heat shield concern is real engineering, not hand-waving, but the first principles question isn't whether risk exists. It's whether the risk is characterized well enough to fly. NASA spent 3 years after Artemis analyzing that heat shield. They understood the erosion mechanism. Gas pockets in the Avco blocks behaving differently than ground tests predicted. They modified re-entry parameters. They updated thermal models. They instrumented this flight to capture data the first mission couldn't. That's not ignoring the problem. That's the engineering method working exactly as designed. You fly, you learn, you adjust, you fly again. The launch sequence itself was textbook. Twin solid boosters producing 7.2 million combined pounds of thrust. Separating on schedule. Core stage cutoff nominal. Fairing jettison clean. Solar arrays deploying all 4 wings. 15,000 cells per wing. Locking into place. The engineering is precise enough that each milestone hit its timeline within seconds. One detail worth noting. A commenter in Europe described their children sleeping on the couch in front of a projection screen, waiting for a half-past-midnight launch. Another watched with their son, having assumed they'd never see humans go to the moon in their lifetime. These aren't spectators. They're participants in something that belongs to everyone. Because the telemetry is public, the mission updates are live. The broadcast streams free on 3 platforms simultaneously. The next milestones are the perigee raise maneuver, an apogee raise burn, then a proximity operations demonstration, where the crew manually flies Orion relative to the spent upper stage. Humans steering a spacecraft by hand near the moon for the first time in over 50 years. The heat shield will either validate the updated models or it won't. Either way, we'll know. That's what test flights are for. 5 stories deep, and we're covering everything from lunar orbit to your inbox. Let's talk about keeping that inbox safe. Matt Mullenweg, the guy who runs WordPress, which powers roughly 43% of the web, almost got phished. And the way it happened is a masterclass in why authentication infrastructure is fundamentally broken. Here's the attack chain. Step 1. Spam Apple's legitimate password reset flow. This isn't a vulnerability in the traditional sense. It's a feature. Anyone can trigger a password reset request for any Apple ID. The system is working exactly as designed. Your watch buzzes, your phone lights up, your laptop pings. You dismiss it. Fine. But now you're primed. Step 2, and this is where it gets genuinely clever. The attackers called Apple support themselves, pretending to be Mullenweg, and opened a real support case. Apple's own systems then sent real emails, cryptographically signed, from real Apple servers, with a real case ID. No spam filter catches these because they aren't spam. They're legitimate Apple communications about a fraudulent request. The authentication is perfect. The intent is the problem. Step 3. A human calls. Calm, professional, gives genuinely good security advice for the first few minutes, builds trust by being competent, then drops a link to auditapl.com, a pixel-perfect replica displaying that real case ID from those real emails, complete with a fake transcript of the scammer's own conversation with Apple, repackaged as evidence of the attack against you. Run this forward. Every component here is a commodity. Password reset, spam is scriptable. Social engineering, Apple support, into opening cases scales linearly with call center labor. Domain registration is instant. Pixel-perfect site cloning takes minutes with modern tooling. The only bottleneck is the human on the phone, and voice synthesis is about 18 months from making that irrelevant too. What saved Mullenweg was clicking around the fake site and noticing any case ID returned the same result. Nothing was validated server-side. It was theater. He told Alexander from Apple support that the phishing was obvious. Silence. Click. The fundamental constraint here isn't user education, though Mullenweg's advice is sound. Never approve unsolicited reset prompts. Apple will never call you first. Always verify URLs. The constraint is that Apple built a password reset system with no rate limiting and a support system, where third parties can open cases on your behalf. The authentication surface area is the product surface area. Every feature is an attack vector someone hasn't thought of yet. Mullenweg published the whole thing, including a recording of the call. That's the builder instinct. Got embarrassed. Shipped the postmortem anyway. Moving on. One of the top comments on this piece is someone saying they just stopped caring. They leave their email in plain text on their website and let their spam filter handle it. And honestly, that's where most of us are. But Spencer Mortensen decided to actually test it, and the results deserve a straight read. He set up honeypot email addresses, each protected by a different obfuscation technique, and tracked which ones got harvested over time. 318 spammers later, the data tells a story that reminds me of epidemiology, specifically herd immunity. In public health, you don't need every single person vaccinated. You need enough coverage that the disease can't find easy paths through the population. Email obfuscation works the same way. You're not trying to build an impenetrable fortress. You're trying to be harder to harvest than the next website. Plain text. Zero protection. Every single harvester grabbed it. 100% infection rate. But here's what's remarkable. Just wrapping characters in HTML entities, the most trivial encoding imaginable, blocked 95% of harvesters. Hiding a decoy span with CSS display, none blocked all of them. Every single one. The reason this works is the same reason herd immunity works. Most of the threat actors are unsophisticated. They're running the equivalent of a common cold, not a targeted bioweapon. Basic bots scraping raw text with simple regex patterns. They don't render CSS. They don't execute JavaScript. They don't parse SVG files. The few sophisticated harvesters that do exist could absolutely defeat these techniques. But they represent a tiny fraction of the threat landscape. Oh, someone in the comments mentioned setting up a targeted address, hidden by CSS so no human sees it, but visible in source. Any mail server receiving messages to that address knows the sender is a harvester. That's contact tracing. You're not just protecting yourself, you're generating intelligence about the threat. What Mortenson's data actually reveals is that the email harvesting ecosystem hasn't evolved much. The arms race stalled. Most harvesters are still running decade-old collection methods against a web that has moved on to SPAAs and client-side rendering. The defenses don't need to be clever. They need to exist at all. The practical takeaway is almost comically simple. A CSS display none on a decoy span. An SVG embed instead of plain text. Techniques any developer can implement in 5 minutes that have a perfect track record against every harvester in this dataset. The tools exist. The data is public. The techniques are trivial. This is a solved problem that most people don't know has been solved. Protecting your data on the web is one thing. Protecting it inside your own infrastructure is another conversation entirely. Mercor, a $10 billion AI recruiting startup, just confirmed it got hit through a supply chain attack on LiteLLM. An open-source library that routes API calls across language models. LiteLLM is everywhere. Millions of downloads a day. And someone from a group called Team PCP managed to slip malicious code into a package associated with the project. The code was caught and pulled within hours, but hours is enough. Lapses. Yes, the same lapses that hit NVIDIA and Samsung. Showed up claiming they'd exfiltrated Mercor data, Slack messages, ticketing systems, even video recordings of conversations between Mercor's AI and its contractors. Now here's where I want to play devil's advocate. The instinct is to say this is an open source problem. Anyone can contribute, anyone can inject, but run that logic forward and you arrive at a strange conclusion. That code you can't inspect is somehow safer than code you can. The malicious package was identified within hours precisely because LiteLLM is open. Researchers at SNIKE could look at the code, flag it, and trace the blast radius. Try doing that with a proprietary SDK. You'd be waiting for a vendor disclosure that may never come, trusting a company's incentive to tell you the truth about their own failure. The real engineering lesson here is about dependency hygiene, and it's genuinely elegant when done right. Package pinning, hash verification, automated scanning on every install. These aren't exotic techniques. They're the software equivalent of checking the seal on a bottle before you drink from it. The craft is in the discipline, not the complexity. What impresses me about LiteLLM's response, beyond the speed of the fix, is that they immediately overhauled their compliance pipeline, dropping one vendor for another with better audit controls. That's a system learning from failure in real time. That's what open ecosystems do. They adapt publicly. The scar tissue becomes shared knowledge. Mercor's spokesperson gave the standard corporate response. Thorough investigation, third-party forensics, communicating as appropriate. Fine, but the more interesting signal is what they declined to answer, whether contractor data was accessed, whether this connects to lapses. When a company that facilitates $2 million in daily payouts to scientists, doctors, and lawyers around the world can't confirm whether those people's data is safe. That's the part that deserves scrutiny. The vulnerability wasn't in the open source code. It was in the assumptions built around it. The fix isn't fewer open tools. It's treating every dependency, open or closed, like it might be hostile and building the infrastructure to verify that it isn't. Moving on. In middle用是就代表随时就参马ten ten的小笔的注所当清楚了。大不来这的文字系的改的工咱们从头了所有法的公求注册。妈妈话大家按时日付入米一是够设的处，就当时入马是怕驱都出来吃。Make things proprietary so the open alternative can't compete. That was the playbook for 28 years. And this month, Steam on Linux crossed 5%. Now 5% sounds small until you understand the engineering that got it there. Proton is one of the most ambitious compatibility layers ever built. It takes Windows executable, DirectX calls, kernel-level anti-cheat hooks, the entire Win32 surface area, and translates them in real time into something a Linux kernel can run. The Wine project has been chipping away at this for decades. Codeweavers turned it into commercial-grade work. And then Valve did something unusual for a company its size. They funded the open-source infrastructure directly, not a proprietary fork, not a walled garden, upstream contributions to Mesa, to the Linux kernel's GPU scheduler, to DXVK. Every improvement Valve makes to run games on the Steam Deck flows back into every Linux distribution on the planet. The hardware story is just as telling. Nearly 70% of Linux gamers on Steam are running AMD processors. That's not brand loyalty. That's an engineering choice. AMD publishes open-source GPU drivers. Their documentation is available. When you're building a compatibility layer that needs to talk to graphics hardware at the lowest level, the difference between an open driver stack and a closed one isn't philosophical. It's the difference between debugging a problem and filing a support ticket and waiting. A quarter of those Linux gamers are on Steam OS itself, which is just Arch Linux with a controller-friendly interface on top. The entire operating system is inspectable, modifiable, replaceable. Valve built a gaming console where the owner actually owns the hardware. The reader comments tell the real story better than the numbers do. People are switching not because Linux is novel, but because it's practical. One user installed Nobara on a living room PC and reported 0 regrets. Another has gamed exclusively on Linux for 2 years. Their only maintenance task is occasionally selecting a specific Proton version. The friction is genuinely disappearing. This is what 28 years of open-source engineering looks like when it compounds. Every Mesa commit, every kernel patch, every Wine compatibility fit. None of it was wasted. The decommoditization strategy failed because you can't out-resource a global community that never stops building. Now for something completely different, we need to talk about quantum computing, because this week dropped some genuinely wild developments. Google just mass-published a quantum computing result by proving it exists without showing anyone how it works. A zero-knowledge proof for a circuit that breaks elliptic curve cryptography. They essentially said, we found a way to factor this. Here's mathematical proof. We're not lying. No, you can't see it. The last time mathematicians pulled something like this was the 1500s. When Italian algebraists would prove they could solve quartic equations by challenging rivals to public duels. Niccolo Tartaglia versus Antonio Fiore 1535. Solve these 30 problems. Loser pays for dinner. The flex wasn't the proof. It was the withholding. But here's where the parallel breaks. Scott Aronson, who got an early look at these results, immediately thought of Frisch and Peierls calculating critical mass for uranium-235 in 1940. They didn't publish either, and the cryptography community pushed back hard on that analogy. Their answer, forged through decades of experience. You publish. If publishing makes people using quantum vulnerable systems panic, maybe panic is the appropriate response right now. 2 papers dropped simultaneously. Caltech showed fault-tolerant quantum computing with dramatically lower overhead using high-rate codes. Applicable to neutral atom and trapped ion architectures, Google showed a leaner implementation of Shor's algorithm targeting 256-bit elliptic curve crypto. Combined, the Caltech group estimates 25,000 physical qubits might be enough to break Bitcoin signatures. A year ago, that number was in the million. The timeline didn't change by decades, maybe a year, but a year subtracted from an unknown number still concentrates the mind. One commenter traced the trajectory. Microsoft estimated 10 million physical qubits in 2022. Now we're at 25,000. That's not incremental. That's the kind of compounding that happens when research is published openly, and every group worldwide can build on the last result. The Bitcoin community has spent years insisting quantum isn't a real threat. The numbers just stopped cooperating with that narrative. Post-quantum cryptography standards exist. NIST finalized them. The tools are available. The algorithms are published. The migration paths are documented. This is an open-source success story waiting to happen. Or a preventable disaster if institutions keep dragging their feet. We talked about building on open foundations earlier, for here's a project doing exactly that for the web itself. 96%. That's the share of WordPress security vulnerabilities that originate in plugins, not in the core, not in misconfigured servers, in the extensions that people install because WordPress alone doesn't do what they need. That number has been climbing for years. And in 2025, it accelerated. More high-severity plugin vulnerabilities than the previous 2 years combined. Cloudflare just shipped an early preview of EmDash, a CMS built from scratch in TypeScript, MIT licensed. Designed around one architectural decision that matters more than everything else in the announcement. Each plugin runs in its own isolated sandbox. A Cloudflare worker. The plugin cannot touch the database directly. It cannot read the file system. It gets an API surface and nothing else. This is the detail worth pausing on. WordPress plugins are PHP scripts with root-level trust. You install one, you hand it the keys. 23 years of that architecture produced an ecosystem where the most useful feature, extensibility, is also the most dangerous. EmDash doesn't patch that problem. It makes it structurally impossible. MIT, not GPL. That's a deliberate choice. GPL requires derivative works to stay open. MIT lets anyone do anything. More permissive means lower friction means more people building. The bootstrapism case is straightforward. The easier it is to fork, adapt, and ship, the more builders you get. The honest caveat, this is a Cloudflare product. It runs elsewhere, they say. Any node server, whether that stays true as the feature set grows is the question worth watching. But the architecture is public, the code is readable, and the plugin model is genuinely better engineering, not just better marketing. This has been your daily tech feed for Hacker News for April 2nd, 2026. This podcast is entirely AI-generated. Scripts by Claude Opus 4.6. Voice by Quen3TTS. Not affiliated with Hacker News or Y Combinator. Now go build something that makes tomorrow a little more open than today. We'll see you back here tomorrow.